Hello. So in this one, we're going to be showing our the test case number 8 for our 8-bit ALU. So the answer should be 7A, and we confirmed that in the document. So here, if we switch it, changes to 3, changes to 5. This changes to 2, changes to C. If we change these, switches everything. Um, so this is the test case um, for the 8-bit ALU, and then if, like I showed, if we switch them back, then it goes back to 7A. And then we are going to break down our logical universe. So that's part one of the of just making it in general. So here we have all our inputs, um, which leads all in the example. Well, from the document, we have to give all these inputs and then send them through all these gates. And then if we go through, I'll show a test case for this one. So for example, if they're all true, then they will all turn on except not be out. So not be out will be false. Actually, in this example, it's this one's false too. So we'll have these, but this is how we approached it. And yeah, we use the light bulbs, and then we have these switches. So this will obviously, when it's switched, it's high. When it's not, it's low. So that means 0, 1, and obviously these AND gates, the OR gates, and then the NOT gates to inverse it. And if we go to the next one, which will be the decoder. Wants a decoder next. Logical unit full adder, 1-bit ALU. Will be here. No. And then here we have our decoder circuit. Right here is obviously the integrated circuit. So here we just have our two inputs that are stated from the document. And obviously in the case where there's two falses, it'll turn on here with this bulb. So obviously we switch it. It switches in now, or in out is high. If we turn on both, it shows that this case is true. Vice versa, switch this one and this one. So yeah, we just took a lot of the help from the actual example, how Professor Grissom described how it gives you basically 90% of the work. You just have to, so we changed all the inputs, made sure they all aligned with what the document was asking for, and then proved our test cases. I can give a specific test case for the decoder. So if both of them are true, like I specified, then add in out. If they're both false, then this one has to be true, and then this is shown through our truth table, which is in our document. So now we're going to open up the last one, which is the full adder. So this is the full adder. Obviously, like again, we have our inputs right here. So again, B in progress and A in progress and then add in. We have our two outputs, some out and C out. These are just toggle switches. These are lights, so they flash when something is true. We have our NOR gates here, our AND gates, normal OR gate, and then obviously just another AND gate, which with 3 inputs. So In these cases, right, it shows when they're all true, it shows that both outputs are all true. Vice versa, if these three are true, then it shows that only C out is high. In terms, I can definitely give a case. So in the case that BIP is false, AIP in is true, C in is false, and then add EN is true, then sum out should be true, and then C out should be false. And then this is obviously one of our test cases that we provided in the document. It just shows that our circuit is working. The truth table aligns with it, and all of our values work. And then this is obviously leads to the 1-bit ALU. 1-bit ALU slice. This is similar to where we this is a previous work in progress 8-bit ALU. Obviously, we already showed the final product, but here we just combined all three, so the logic unit, the decoder, and the full adder. And then from there, we just integrated the circuit and then followed the rubric of Professor Grissom, where he wanted all his inputs, his outputs out, and then A0 or 8x in, bx in, and arithmetic x out, following the rubric. So those are all our test cases. The 8-bit adder, the 8-bit 8-bit slice. We showed how we got there through the logical unit, the decoder, and the full adder. And then how we went to the 1-bit ALU. Going more into depth about the ALU. Obviously, all this is relating to and following the example on the project document. But here we have our defined outputs. So arithmetic out, C out, F0 out, F1 out, and then this is our full adder, the logical unit, and the decoder. And then obviously these are all our inputs that are defined. So in total we have to have, I believe, seven inputs and then 7 outputs, but they're all aligned here, and this just relates. So then and then obviously we already broke down the logical unit. It's the same. Breaks it down, and then it sends all these outputs to an OR gate with sum out also leading here. Most of the outputs from the logical gate go back into the logical unit, while with one going back into the full adder, and then one going just straightly directly to an output. So the F1 in goes into the decoder, but it's also its own direct output. Similar to this one, C in goes directly to the full adder. And those are all the cases we broke down. How it is that we actually built the 8-bit ALU, going from the logical unit to the decoder to the full adder to a simple 1-bit ALU. How we put 8 of those in series, combined them, and then got out our designated binary numbers based on our test cases. Thank you.